So this was presented to the Water Projects Committee last Thursday. About 25 slides. They brought the reports and stacked them up on the table. And we spent close to 2 hours. I cut it back in half, and I can do it in 15 minutes or 20. It's up to you guys as to how many questions you have. The outlines for the presentation is I want to give you a summary or an overview of the preliminary design. And I want to point out that there's this new pump back feature that wasn't in the project when it was conceived back a year or two ago. And that will increase the dry year production, and I'll explain why and how much. I want to give you the highlights of the groundwater model results that we've evaluated, and then a capital cost update. I also want to highlight the value of the surplus water. So we pump back to the East Branch, we pump extra water out of the groundwater bank in dry years. There's a value to that which we can estimate over time. And then, since we performed the CEQA initial study, we have a draft mitigated make deck to go out to public review. We're here to get your approval to issue that document to the public later this week or next week for a 30-day review period. I want to go over the project schedule and then talk about the next steps, which is the design and the bid assistance phase, so that we can proceed with that portion of the project. And there's a recommendation for the board. So with that, this diagram shows a plan view with north to the top of the page. And what it shows along the bottom, if you will, is the East Branch. And on the left is 96th Street, and on the right is 116. So the property shown in the upper left is the 80 acres that you purchased for construction of the water bank. In order to deliver water to the bank, we take it out through an existing turnout with modifications. And from that turnout, we would run a pipeline, 20 or 24-inch pipeline down 96th Street and over to the project site. The project will have 3 recharge basins, and I'll show you more details of that on the next slide, and 4 wells. Those wells will pump water out, potable groundwater, which can then go approximately 2 miles through a 20-inch diameter pipeline over to the Eastside treatment plant and into the Clearwater. This water can supplement production from the Eastside treatment plant or completely replace at any time you like the production from the Eastside treatment plant. And by substitution for a quarter, you can run lower THMs, you can lower your annual average to help meet EPP regulations. Anytime that the water quality in these branches is poor, you can trigger yourselves to switch supply, so you have an alternative supply. Plus you have a water bank that can provide water in dry years like this year, if you have been banking in this project as you have in your other. So that's an overview of the layout. And so if we take the project site on the top left and we tip it on its side so it fits on the page better, we have this diagram.
Hey,
so
come
now
on in,
north
that's okay.
is to the left. And the street on the right, so it goes in front of Scategliella Farms, it's Avenue U, and it turns into a dirt road in front of the site. So again, in the middle of the site, we're talking about, is this actually the point?
You have to use the mouse.
All right. So these are 3 recharge basins, and they actually sort of staircase down the hill about 7 feet each because the site slopes slightly. They're cut and filled, nearly balanced earthwork. Basically, they're infiltration ponds. So by delivering the water to the site from the East Branch Canal by gravity, it actually goes into a box, which we call a splitter box. And then your operations folks can deliver the water to any one or all of the basins at any given time. And each basin is designed to take the full flow, so you basically have a spare or 2, depending upon the infiltration rates. So, and these wells are expected to be drilled to 500 or 600 feet, with the exception of the southeast corner, which might be more shallow, based on some previous work we did just down the street. Each well would pump into a 12-inch pipeline and be collected on the site into a 20-inch pipeline, and as I said, run over to the Eastside plant. Each well also has a blow-off line, and the blow-offs actually group together, and you can pump the blow-off into an oversized blow-off pond, which will hold 3 hours worth of water for a pump test, if you will, which you can also overflow that into the same basin, so you can run any of the wells for any period of time, like 24 hours if you need to do some periodic sampling or something. It's a benefit to have a place to put the water without it leaving your site. There's a building on the front of the site, which I'll show you a schematic of. And so basically we cover the fact that there's piping, recharge basins, 4 wells, those are major facilities. And in the front of the site, there's a building and a small tank. The building has a dual purpose. It's both a chlorine storage and chemical feed room on the right and a pump station on the left. And why a pump station? The wells will produce water and deliver it through a pipe conduit, if you will, all the way to the tank, and that's potable water supply. But if we want to take a portion or all of the water and send it back in a raw water pipeline to the east branch, we need to separate that from the public water system. We do that through an air gap, which is required by the Department of Public Health, CDPH. So basically we have this tank right next to the building where the water will go through an approved air gap, and now it's no longer potable supply. It's basically turned back into raw water, and it can be pumped through these vertical turbine pumps, which are 2+1 standby, and they can each pump 5 million gallons a day, and they would pump back to the east branch. The purpose of this is to be able to leverage the production of more water back out of the water bank. Now, this is the model scenarios that we ran in the model. When we had run the model some time ago, we had the top scenario, we're calling it the previous scenario, if you will. So we're only water banking at that time about 4,000 acres per year. We were taking up 1,200 acre feet in 7 out of 10 years. In 3 dry years, we were extracting all the water that's consumed in the Eastside service area that we would otherwise deliver by the treatment plant, which is estimated about 5,500 acre feet. So in 3 dry years, we produce about 16,500 acre feet. And that's good because that's water you wouldn't otherwise have available. It wouldn't have to come from the state water system. Now, the total recharge in that previous scenario was 28,000 acre feet. Total extraction was about 25,000 acre feet, roughly 90%. Now, with the new scenario where we can pump back to the east branch, we can actually produce more water in those 3 dry years. So now we've increased the recharge to 6,800 in 7 years. We still take out the same amount in those 7 years. Now, during the 3 dry years, we can extract more water, 11,500. In so doing, we have you banking 48,000 acre feet over the 10-year period, taking out 90% of that, or 43,000 acre feet. What this does is gives you an additional 18,000 acre feet of supply in those 3 dry years. So basically, it leverages your ability to use the existing infrastructure in the 4 wells that you have, so you can bank more water and you can extract more water, so you can leverage the water bank more. But we did model that to see what are the levels that would rise in the ground and what are the drawdowns that we would get from the current water levels. Now, when we run the model and we put water in for 6 years, significantly more than what we take out, water mounds up and you create like this big hill, if you will, underground. And these are the contours. And so the water rises 60, 70, 80 feet in the center, higher than it is now. So if the water's at 175, it'll come up to about 100 or 90, 100 feet, still significantly below the surface. Now you turn around, and in 3 dry years, you pump out the quantities that we just mentioned, and it drops the first year, it drops in the second year, and it drops in the 3rd year because you're no longer recharging. So you're pulling all your water out. And in doing that, did it move or is it? Let's see. This is a contour map. The circles being, the rings being 5-foot contours go in the opposite direction. So this is the depression that you would create by running for 3 years without recharging. And this is the maximum scenario. This is the extremes of what we'd expect to be the maximum mound and the maximum drawdown. And you can operate the bank at levels in between without going to those extremes. So we want to model the maximum so that you can see what the variations are. In this corner, the southeast corner of the 80-acre site, we have an elevation that indicates the bedrock might be higher because about a half mile to the east we had done some geophysical testing. When we were looking for properties, we were doing geophysical testing along the street right away. And we found an area that was more shallow, like about 450 to 150 and back. So we took that ridge line and assumed that it was equal to the test well we drilled in the middle of the site. So we drilled a test well in the middle of the site to 607 feet. This is excellent. The neighbor's well is 530 feet. So 3 of the wells we expect to be between 530 and 600, so it's really good for production wells. This one well we expect to be shallower. That's the cost of the project, which is larger than it was before because the project's now larger and it has greater capacity. So some of you may recall that the project was around $8 million when we talked about it almost a year ago or less, really, late summer. Right now, the recharge basins, access roads, site improvements, fully fencing the site using small well buildings, $1.2 million. Drilling and equipping 4 wells, $3.5 million. The pipelines, 3 miles of large diameter, and on-site pipelines, about $3.2 million. This chlorine building, which was previously, we were going to use the Eastside chlorine system, but it would need to be expanded. There's no place to put it. We have to run pipelines across the Eastside site, so we decided a building here would be better along with this new pump station in 10. So the $1.2 million is completely new, and if you mark it up 10%, as you can see, plus engineering approaches $1.5 million. So half of the increase is due to the fact that we developed the front of the site to have a dual-purpose building in the tank that wasn't there before. But then you get to more than double the extraction over 3 dry years. So we feel that this is of great value to the project. So basically, it's a $10 million construction project and $11.4 million when you include engineering, design, and construction management. As we've done before, we have been asked to look at estimating the value of this dry year yield, if you will. So we have done this before for you on other project sites where we assume that if you have to purchase water in a wet year, you've got to go buy it and transport it. It's more expensive than your normal water. Here we've estimated it to be $500, which this year is actually higher. We've seen auctions for $1,100 and $1,300 for water in the marketplace along with East Branch. But assuming the $500, because that's what we had assumed before, and assuming
You need to move faster. Along with what branch?
along the East Branch, there was some recent above in Kern County, I understand, there was some water bank water that was some farmer yield.
Okay.
You had this sale. People were bidding to move the water with more supply this year. Limited supply.
That's not East Branch. That's not East Branch. That's why I was confused.
So wasn't it?
No, East Branch is over here. That's why I just want to know what you talk about on the other side, north of the attachments.
All right, so my mistake.
That's
I
okay.
thought it was lower down.
No, I was hoping you were right.
No, sorry.
No, I mean, yeah.
All right, so water is more valuable than $500 in an extremely dry year. But if you assume 3 dry years out of 10, the water's at this price, and you repeat that over 10 years, 20 years, 30 years, and 40 years, and bring that to net present value, the 40-year savings is like $13.6 million. So the savings would be even higher if the water price was higher, and this doesn't escalate the water price. So that extra water supply of 18,000 acre feet, which we take out and pump back to the East Branch, in 3 years out of 10, for 4 decades is 72,000 acre feet. So that's a benefit of having the project with the tank and pump back the station that we didn't previously have. So it gives you more advantage, if you will, to the storage system. So we wanted to bring that to your attention because of the project. This is a schedule that, since the meeting last Thursday, we've actually shortened at the request of staff because we had a discussion about starting in April, stringing out the 24 months, and without too much effort, we can actually start tomorrow. And the well design is simply 5 or 6 weeks, and you can come back to the board for authorization on the street or delay. You go out for 30 days for the bids. And so when the bids are acceptable, award them at your second board meeting in May. And then environmental, those biology surveys will be done by the 30th of June, assuming that they're negative, then we just proceed. And before you actually award the bid, you have 2 of 3 surveys that are required by the state in one of those species. Then there's an 8-month construction period to drill 4 wells at about 2 months each. So the first couple wells are done and pump tested. We'd use that to lock in the pump curve and the motor size for the remaining wells, which could then be changed if necessary to addendum for one and as a change order for the other. But once the wells are sized, we expect very little variation, very little cost impact.